Hello, everybody. Welcome to Plate Tectonics lecture number 2. I have my still have my lava lamp here. Now it's actually starting to convect, just like the mantle, right? So remember, mantle convection is what powers plate tectonics, and we're going to be continuing along with our discussion of plate tectonics. I'm looking for my oh, here it is, my lecture assignment packet. So we're on number 19, lecture assignment number 19, and we had just gotten done last time talking about how new seafloor is created at mid-ocean ridges. So that's actually the answer to number 1, right? Where is new seafloor generated? It's generated at mid-ocean ridges. And we're going to talk about the other kinds of tectonic boundaries that are called subduction zones. So we'll get into that, all about that today, okay? Got to get my pen working here. It always is a little bit buggy. Pen, here we go. Okay, now it's working. So remember, we're creating mid-ocean ridges here where the asthenosphere is welling up, okay? It's convecting, it's welling up at the mid-ocean ridge. It creates the mid-ocean ridge, and it creates the seafloor, right? The ocean crust that spreads here. And now it's going to move along and spread along, and it's going to die at these subduction zones. Okay, subduction zones are very special places on Earth, and we're going to spend a lot of today talking about those subduction zones. So there are 3 kinds of boundaries, and that's actually the official subject of today, is talking about these 3 kinds of tectonic boundaries. Okay, the first boundary is called a divergent boundary. The next is called a convergent boundary. The next is called transform. So that's the answer to question number 2. Okay. Question number 1. Remember, where are the ocean crust created? It's created at the mid-ocean ridge. Where is it destroyed? It's destroyed at subduction zones. So that's what we're talking about. Now, what is a divergent boundary? Divergent boundary is a boundary that is separating, is pulling away. So the 2 tectonic plates are separating and moving. What's happening at a divergent boundary? It's the opposite. Convergent boundary. They're coming together. Convergent, they come together. Divergent, they pull apart. Transform is when they slide horizontally past each other. Okay? Divergent pulls apart. Convergent comes together. Transform slides horizontally past each other like that. Those are the 3 kinds of boundaries. Now, these boundaries are very important because that's where we get earthquakes and volcanoes. Okay? We'll be talking about earthquakes and volcanoes in the last few weeks of lecture here. Now, earthquakes, if this is a really neat map, take a look at this. This shows all of the earthquakes over magnitude 5 that have occurred since 1960. And you can see that that map looks an awful lot like the map of tectonic boundaries. Why? It's because earthquakes happen on tectonic boundaries. That's why. So you can see that, of course, there's some examples of earthquakes that happen within the boundaries, right? You can see them happening within. But you see, for the most part, they're happening on the boundaries themselves. I want to take a look real close here. Notice that there are, now you can see the outline of Africa right here, right? Notice there are a lot, and here's Saudi Arabia, right? You see that? The Arabian plate. Take a look at this. There's a whole bunch of earthquakes right here, kind of going down the middle of Africa. They would be about right here. Okay, see that? You'll notice there's not a plate boundary there, right? That is the East African Rift. And pretty soon, geologically speaking, that's going to be a new plate. Africa's going to rift apart. There's actually going to be a new ocean that's going to start in the middle of Africa. Someday, millions of years in the future, not today, but pretty soon that's what's going to happen. So we'll talk more about that later. Earthquakes, they happen on tectonic boundaries, but volcanoes happen there too. So of course you know that most volcanoes, 80% of volcanoes happen on mid-ocean ridge boundaries. But also subduction zones have a lot of earthquakes as well. So you probably heard of something called the Ring of Fire that surrounds the Pacific Plate. That's where a lot of the, I can say, above water, the ones that are on the ground, not underwater, but above the water, that's where a lot of the above the water volcanoes are happening. The ones that we actually see and care about. we don't really care very much about the volcanoes that happen under the ocean, even though they're happening every day. We don't even pay attention to them. But we do pay attention to the volcanoes that are happening above the water, right, on land. So volcanoes happen on the boundaries as well, okay? So there are your three kinds of boundaries: convergent, divergent, transform. There are two kinds of convergent boundaries we're going to talk about. There's two kinds of divergent boundaries we'll talk about too. But we're going to talk about continent convergence. That's where two continents collide. We're going to talk about ocean-continent. That's where a ocean plate collides with a continental plate. All right, so before we even get into that, though, let's do divergent boundaries. So we have two kinds of divergent boundaries. The first is an ocean-ocean one. That's where two ocean plates are ripping apart. That's called a mid-ocean ridge. And then we have where continents are rifting apart, and that's called a rift zone. Okay, that's exactly what's happening, like I pointed out, in East Africa. East Africa is rifting apart, rifting off of Africa. Okay, so the Horn of Africa is actually rifting off of it. This is a really interesting geologic phenomenon that's happening right now with the rifting of Africa. It's pulling apart. And it creates these things called rift valleys. We'll talk more about that again in a little bit. But anyway, mid-ocean ridge is extremely important. Why are they so important? That's where new ocean floor is created. Okay, it's where new ocean floor is created. It's where the seafloor spreading is occurring. That's what's pushing the continents further and further apart. Do y'all remember this stuff? Does this look familiar? All this black and white barcode-looking lines. What are those? Do you remember what those are? It's the magnetic anomalies. So that's the record of magnetic anomalies moving away symmetrically from the ridge, right? Normal, reversed, normal, reverse, normal, reverse, right? Looks like a barcode, and it's exactly the same on either side of the floor. Okay, so mid-ocean ridges, that's where new seafloor is created, and it is a divergent plate boundary. Now, I want to talk about, looks like number 5. How is new ocean crust generated? What causes the volcanism there? Okay, we've been talking about ocean crust being generated at mid-ocean ridges, but I haven't talked about how that happens. This is how it happens. It's called decompressional melting. I want you in your mind to connect decompressional melting, connect it with mid-ocean ridge, MOR. Okay? Decompressional melting is something that happens at mid-ocean ridges. Now, you might remember from our igneous lectures that there are 3 ways of melting the mantle, right? There are 3 ways. Do you remember this stuff? One way is to increase the temperature. Do you remember these diagrams? I hope you remember these, okay? They're temperature pressure diagrams, okay? It's showing the line right here is the melting curve of the mantle. The melting temperature of the mantle increases with pressure. It gets harder to melt the mantle as the pressure kicks up. So how do you melt the mantle and make new melts, make new seafloor? There's 3 ways. You can increase the temperature. Okay. You can increase the temperature. But you can decrease the pressure without changing the temperature at all. Does that make sense? Does that surprise you? You can melt the mantle without changing the pressure or without changing the temperature at all. You can melt it. You can see our lava lamp convecting now, right? As the material, the wax, goes from the low end, right? The deep mantle. It convects, it reaches the upper mantle. What happens to the pressure? The pressure decreases. And as it decreases, it melts the mantle. Oh, gosh. That's me. I'm talking. I'm saying some other thing. I gotta hold on a second. I'm sorry for this. Gosh, oh my God. Oh, there I am in the last lecture. Sorry for that. How did that come on? Okay. Anyway, so how do we melt the mantle at mid-ocean ridges? decompressional melting. Lowering the pressure of the mantle. That's it. Okay? How are we lowering the pressure of the mantle? Well, as the mantle splits, or as the crust splits apart, it thins. It gets thinner. It's pulling apart. Imagine taffy, pulling taffy apart. As you pull the taffy apart, it thins out. And as it thins out, it decreases the pressure. Okay? Another aspect of this is as the mantle convects, and the material goes from deep within the mantle where the pressure is high and convects and rises up to the surface where the pressure is low, it keeps the same temperature and the same pressure. It has the same heat, it has the same heat, but the pressure decreases, and that is what causes the decompressional melting. Decompressional melting at mid-ocean ridges, okay? That's how the mantle melts. All you got to put for number 5 is decompressional melting. That's it. So this creates a huge amount of volcanism at mid-ocean ridges, and guess what? That's where heat is released from the Earth, mid-ocean ridges. This is something I want to impress upon you. I want you to understand here. Plate tectonics, think about it as it's Earth's way of sweating. Why do you sweat? Oh, you sweat when you get hot. That's your body's way of cooling. Most animals need some way of cooling. You know that dogs pant. That, other animals have big ears or big flaps of skin that help to circulate blood, to cool the blood down. Humans sweat. That's how we cool down. How does the Earth cool down? Plate tectonics. Plate tectonics is Earth's way of cooling itself off. It's hot inside the Earth. It's really hot. 6,000, 5,000, 4,000 degrees Celsius. Really, really hot. The heat that comes up from the core mantle boundary, it's released at the mid-ocean ridges. So this is a map of energy release from the Earth's surface. And where is it high? It's high along the ridges. Okay, it's high along the ridges. Mid-ocean ridge. So this is the Mid-Atlantic ridge there. This ridge here is the East Pacific, or the Indian ridge system. There's actually 3 ridges that converge in a triple junction in the middle of the Indian Ocean. There's also the East Pacific rise. Okay. So that's the amount of heat being released. And you can see that the heat being released is about and this is milliwatts per meter squared. So it's 132 to 1,237 milliwatts per meter squared. Okay, that's about 50 to 100 light bulbs burning on a football field. It's not like a tremendous amount of energy, but it's enough. So divergent boundaries, talked about mid-ocean ridges. I want to talk about some places where ridges are forming right now. So this is happening right now in California. So if you look, you might know about Gulf of California, right? Baja California right here. You might notice that it almost looks like the Baja California is splitting off of mainland Mexico, and it is. Okay, so think of it almost like a zipper. This thing's zipping right along. There's a mid-ocean ridge starting to develop right in the middle of the Gulf of California, which is that thin little gulf of water here between mainland Mexico and Baja California. And if you take a look, this is kind of interesting. Take a look at the satellite view right here, okay? You're looking south. You're hovering over like Los Angeles and you're looking south. You see the Gulf of California here. And notice what we see as we move along. We see this big lake here. This is called the Salton Sea. It's in Southern California. What's happening? Why is there a sea there? That is the beginning of the ocean starting to come and flood inland because there's a valley here. There's a valley. So it's dropping down, it's thinning out, it's pulling apart, and as the taffy stretches, it thins out and it drops down, and you get a valley, and it starts filling up with water. Okay, so pretty soon that's going to zip all the way. The Gulf of California one day is going to extend all the way up to San Francisco. It's going to pull apart, and then that's all going to split off of mainland, mainland USA, mainland California. But of course, we're talking about millions of years in the future, a million years in the future. We're not talking about tomorrow. Same thing's happening in Africa, right? It's thinning apart. You might notice right here, there's a lot of lakes in Africa. So first of all, you have the Red Sea. Okay, you have that. And then look at this. You have lake. Connect the dots with the lake. Lakes, Tanganyika. This is Lake Malawi, Lake Tanganyika in Tanzania. You have Lake Victoria. Okay, all of the lakes. And guess what is forming right there? That's the East Africa Rift Zone. So as the crust stretches, pulls apart, the taffy's pulling, it thins out, it stretches, it extends, and the elevation drops. And then water comes. Okay, that creates the valley. And then water loves valleys. Okay, water loves that low elevation. It always goes and flows towards low elevation. So that's why the lakes are forming there. Same thing with our Great Lakes, actually. Guess what? Our Great Lakes all were forming there because there was an ancient rift valley. It's about a billion-year-old rift valley. But it failed. It never actually pulled America apart. But it started to rift apart. That's why Lake Superior and the other Great Lakes are where they are. That's why Lake Superior is so deep. Lake Baikal, the deepest lake of the world. Again, it's a rift valley lake. Here's a rift valley really close to us, the Rio Grande. Why does the Rio Grande go where it goes? You all know the valley. People talk about the valley. What valley is it? It's the Rio Grande River Valley. It's pulling apart. Someday Mexico and America are going to be pulled apart, and that valley is going to get deeper and deeper. And it's, one day, maybe if it's successful, it's going to pull apart. There'll be a new ocean there. Okay, so that's a rift valley. Same thing, there's a failed rift that goes along here in Missouri, Kentucky, Arkansas, Tennessee. There's a failed rift valley. It's about 600 million year old failed rift valley. That's why the Mississippi River flows where it flows. Why? Because the crust is stretching, it's pulling apart, and as it pulls apart, thins out, and that's where the water starts to collect because the elevation goes down. Water always goes downhill to the lowest elevation. Okay. So anyway, I think we covered now number 8. Talked about number 7. I gave you a lot of real world examples of where we get divergent plate boundaries. Any mid-ocean bridge is good with that. I want to talk about a little bit about number 9, basin and range. Basin and range. So what is basin and range? I want you to take a look at this map of America. It's a topographic map. That means it's showing the mountains and the valleys. And you'll notice that there's a big part of California, Arizona, Oregon, goes all the way into Utah. Actually, some of it even extends all the way into Wyoming. But it's a big section of the Southwest that has this kind of strange look to it. I want you to pay attention to how this looks. You see how there's all these kind of wrinkles? You see these? All these wrinkles in the surface? And they're all kind of trending in the same direction. They're all kind of going somewhat, maybe a little bit off of north to south, but maybe like a little bit northeast to southwest. They're trending in that direction. So you see all those wrinkles, I hope? Okay, what is all that? That is called basin and range. Basin means a valley. Range means like a mountain range. You'll see there's all these series of mountain range, mountain range, mountain range, basin, mountain range, basin, mountain range, basin, mountain range, basin. See, so that's what it looks like. Looks like this. Here's a really good example of that in Nevada. Okay, basin and range. So you just see mountain range, basin, mountain range, basin. That is a place where there is extensive extension going on in America. Now, the reasons for it are very deep, and I have a whole lecture about this. If you ever take historical geology, I talk a lot about this. But I just want you to know that in the Basin and Range province, that is an extensional regime. Okay, there's extension happening, and that's what creates the basins and the ranges. Okay. It looks like I kind of screwed up number. I'm actually looking at this now, and I realize I made a mistake, little typo here on your lecture assignment, because it says, what is happening in the Basin Range province, crustal shortening, crustal extension? What are two kinds of convergent boundaries? That should be a new question. What are the two kinds of convergent boundaries? So I apologize for that. But anyway, let's talk about those two kinds of convergent boundaries. So you know that divergent boundaries, pulling apart, mid-ocean ridges, decompressional melting, creating the seafloor spreading, right? That's what's happening. If seafloor is spreading, the seafloor is being created, it has to be destroyed somewhere. It can't just create bigger and bigger and bigger shell of Earth, right? We need to have it destroyed somewhere. Where is it destroyed? The seafloor is destroyed at subduction zones. Divergent boundaries create the seafloor. Convergent boundaries destroy the seafloor. Subduction zones are just special, magical places. They're just awesome, okay? Subduction zones are the graveyard of ocean crust and the nursery of continental crust. Subduction zones are the graveyard of ocean crust, the nursery of continental crust. What does that mean? Subduction zones are where the ocean crust goes to die. And from its death, the continental crust is created. And I'll explain that now. Subduction zones are basically when the ocean lithosphere, ocean crust with the lithospheric mantle, gets cold. And when it gets cold, well, actually, let me start here. It gets old. 180 million years is when it starts getting too old. Gets old, and as it gets old, it cools down. You know, when it first starts off, it's hot. It rises up and it cools down. What happens when the wax here, my little lava lamp, what happens when it cools down? It starts to get dense. And when it gets too dense, it starts to sink. So I bet if I put some ice up here, boy, you could really make this stuff start dropping down fast, right? So it gets old. The wax up here gets old. It gets cold, and it starts to sink again. Exactly the same thing happens on Earth. It gets old, it gets cold, and it starts to sink back down. So that's what happens at a subduction zone, okay? So continents don't plow through the mantle. They drift passively with the currents of mantle convection, okay? So there's an upward current, there's a downward current. And the downward current is the subduction zone. Now, let's talk a little bit about active and inactive margins. So subduction zones always happen at the margin of the ocean crust and the continental crust. Now there are two kinds of margins. You have an active margin, that's a subduction zone, okay? So that's subduction. But we also have passive margins. That's where there is no subduction taking place, or there's no plate tectonics taking place at all. So active margins are places like the west coast of South America, the west coast of North America. Those are active margins. The east coast of America and the east coast of South America are passive margins. Okay? That means there's no active plate tectonics taking place there. Now, at an active margin, a subduction zone, what do we see? Let's go through this diagram. The oceanic lithosphere with the ocean crust starts to sink. It gets old, it gets cold, it starts to sink, and it sinks into the mantle. Now, I want you to imagine something. This ocean crust has been underwater for 180 million years. During that time, a lot of water has seeped into it. It's soaked into it. Water, 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 water. Okay, it's seeped in. It's like a sponge. That sponge gets subducted, and the heat and the pressure push the water out. When it pushes the water out, the water acts as a flux. It is a flux, and it causes flux melting. What is a flux? A flux is anything that changes the melting or lowers the melting temperature. Okay? People that do like, maybe you've seen this before. People do like soldering. You ever heard of that before? Soldering like metal wires or whatever together. They add a flux to lower the melting temperature of the metal so that they can melt it more easily. Okay? A flux lowers the melting temperature. You are already familiar with a flux because probably you have heard of using salt to melt ice. Like if there's a snowy, cold day, you throw salt on the ice to melt it. That is very similar to what water does to the mantle. Salt is to ice as water is to the mantle. Salt melts the ice, it lowers the melting temperature of the ice. Water lowers the melting temperature of the mantle. Causes flux melting, causes volcanism, and it creates what's called arc volcanism. We call subduction zone volcanoes arc volcanoes. And the reason that we do that is because these are often shaped like arcs. Okay, I'm trying to see if I can find some really good examples of that, but I don't think I put anything up. But I'll give you I guess I can give you some good examples here of arcs. The Aleutian Islands right here, that's an arc, right? You see how that makes an arc? There's the Puerto Rico and the Puerto Rican plates here. That's an arc. That's arc volcanism. Japan, you ever notice how Japan is kind of shaped like an arc, right? It's the same thing. Sumatra in Indonesia shaped like an arc. So that's why we call them arc volcanoes, because those places I just mentioned are all subduction zones, and they all have arc volcanism. All right, now at the place where the old ocean floor is sinking into the mantle, we get a trench, a very deep trench. It's the deepest part of the mantle. Deepest part of the ocean, can get up to 35,000 feet deep. This is also a place where we get the deepest and strongest earthquakes occur at subduction zones. They are very dangerous places in terms of seismology. Okay, it's the most dangerous place to live in terms of earthquakes, or anywhere where there's a subduction zone. Okay, it creates a lot of earthquakes. All right, so one last thing I want to point out here. There is a wedge of sediment that forms right here as the ocean crust is subducted. That is all the sediment that gets scraped off of the top of the plate as it goes into the mantle. And that wedge of sediment is called the accretionary wedge. Call that accretionary wedge. All right. So anyway, one really cool thing that we can do is we can actually do seismology and measure earthquakes that are occurring in a subducting slab. So if you go to South America, do seismology in South America in the Andes, you'll find that earthquakes here on the coast are very shallow, no deeper than 50 kilometers. But as you go progressively inland, they get deeper and deeper and deeper and deeper, all the way down to 700 kilometers. Believe it or not, we can actually measure the size, the faulting and the earthquakes that are happening on subducting slabs in the mantle. We can measure them 700 kilometers deep. So it shows to you the truth of subduction zones, right? That really is going down there like that. We can actually map it out with the seismology. We call these areas, by the way, where the plates are sinking down very deep into the mantle, Wadati-Benioff zones, and we'll talk more about those when we talk about earthquakes. All right, one thing I want you to pay attention to is, and by the way, I've talked about number 10, talked about number 11, talked about number 12, okay? Talked about number 13. One thing I want to show you here, this is a map showing active subduction zones in the world. And the blue stars are places where there have been the largest earthquakes known to man so far, magnitude 9 earthquakes. The blue stars show where there have been magnitude 9 earthquakes. Now take a look at this, folks. Where are the magnitude 9 earthquakes at? They're on the subduction zones, right? They're right there at the subduction zones. Question for you all. Do any of you see a red subduction zone that does not have at least one blue star? Take a look. If you noticed the Pacific Northwest of our country, you would be correct. We have not had an earthquake there, a magnitude 9 earthquake there, since maybe the 1700s. We know that. Of course, this was before European settlers came, so we don't have like any kind of records, because the Native Americans who were living there didn't keep written records. They didn't have a written language. But from like oral traditions, there are stories of great tsunamis and things like that happened. And we can also look at maybe like sedimentary records that were left over from the 1700s. And we can kind of piece together that we think that maybe sometime in the 1700s, from history, from the stories, from the sediments, that maybe there was a tsunami and maybe a magnitude 9 earthquake that occurred there. So it's been a long time. It's long overdue. Subduction zones have the deepest, strongest earthquakes. That's where we get the magnitude 9 earthquakes, the real big ones. Okay, so these always create tsunamis. Without exception, they create tsunamis. Very, very dangerous situations. Tsunamis kill really a lot more people than the earthquakes do, and they kill a lot more people than the volcanoes do, right? So very, very dangerous. So anyway, I hope you've labeled number 13. I hope you've given number 14, given some characteristics of an ocean-continent convergent boundary. Maybe you've able to do number 15 in just a second. We're going to talk about continent-continent convergence. However, one thing I just want to drill into again, I asked a question here, number 11. How do volcanoes form at subduction zones? Describe the process. How the mantle and the crust melt at subduction zones. How do they melt? They melt due to water. Water from the subducted ocean crust gets into the mantle, and it lowers the melting temperature of the mantle. Okay, and that's what causes the melting. The temperature doesn't change. The pressure doesn't change. I'll say it one more time, because no matter how many times I say this, a lot of people still just don't get this. It's so hard to understand that you can melt something without changing the temperature, but you can. Okay, think of melting ice with salt. The temperature doesn't change. The pressure doesn't change. It's all the addition of water to the mantle that changes the melting temperature, that causes it to melt. Okay? So it happens by changing the melting temperature due to a flux, which is water. Okay? So the water isn't superheated. There's no change to the temperature. Well, in fact, if there is any change to the temperature, it's a cooling. Okay? It's not an increase in temperature. It's a changing of the melting temperature. All right, so that's number, and we call that flux melting, creates arc volcanism, and water-rich sediments descend into the subduction zone and add water as a flux. So that is the answer to number 11. Hopefully you can remember that for the test. All right, I will most likely ask that on the test, just FYI. All right, so it's been a long time since we've had a big earthquake in places like Portland, Oregon, or Seattle. They estimate that in our lifetime, probably in your lifetime, there's a 1 in 5 chance that Portland, Oregon could get hit by a magnitude 9. It would be devastating for that city. That city is not prepared for a magnitude 9 earthquake, because we haven't experienced it, in so long. When it happens, people will realize that it's needed, but it's not prepared. So it's going to be probably one of the worst, if it does happen, probably one of the worst earthquakes in most destructive earthquakes in U.S. history. So anyway, something to look forward to, I guess. But remember these characteristics of a convergent plate boundary: strong, deep earthquakes, mountain building, arc volcanism. All right, let's talk about continent-continent convergence. We have a very good example of continent-continent convergence happening today in India, where India is hitting the continent of Eurasia. right? It's running into it, and it is creating mountains, and it's creating some of the highest mountains in the world, right? India was not always connected to the European Eurasian landmass. It hooked up about 10 million, well, maybe not 10 million years ago, maybe 20 million years ago. It started to make contact, and it's been colliding ever since. Okay, 71 million years ago, it was an island. Okay, and so it's been colliding with Eurasia and creating what we know now as the Himalayan mountains. Okay, so the Tibetan Plateau, it's the Indian plate is colliding with the Eurasian plate, and it's creating the Tibetan Plateau, uplifting Tibetan Plateau. So this is a place where we get very, very, very heavy uplift, heavy mountain building. This is what creates the very bad earthquakes that can sometimes happen in 2015 in Nepal, other places in China. Where's the tectonic force coming from? It's coming from this collision of India and Eurasia. Okay, so no volcanoes there, but heavy mountain building. All right, so let's talk finally about transform boundaries. They're not as important for understanding plate tectonics. Transform boundaries, again, it's horizontal sliding past each other. Okay, it's where the plates are sliding past each other. One place where this happens in a very big way is in California with the San Andreas Fault. San Andreas Fault system is a series of faults that run all the way from Baja, California, like I said, all the way up through San Francisco. And again, it's just a horizontal sliding. It's called a right lateral fault. The reason it's called a right lateral fault is because if you are standing right here and you look towards the other side of the fault, you'll notice that everything is moving to the right. And if you stand on this side of the fault and you look at the fault, you'll notice that everything again seems to be moving to the right on the other side of the fault. So it's called a right lateral strike slip fault system. It's a transform boundary. Okay. Now how fast does all this stuff happen? You can see with our convecting lava lamp, things are happening very fast. But how fast do things happen on Earth? Well, convection happens very slowly. It's only happening about 1 to 10 centimeters per year, which is about how much your fingernails grow per year. Okay, so it's very, very slow. Some places it's faster than others, but it's very, very slow for the most part. Okay, so anyway, that's all I think I have for you today. Here's a few test questions to test your skills on. Deeper than 50-kilometer earthquakes occur at divergent, transform, or convergent boundaries. They happen at convergent boundaries, at subduction zones. Deepest and strongest earthquakes happen there. Volcanism does not occur at a, divergent, ocean convergent plate boundary, ocean-continent convergent plate boundary, continent-continent plate boundary. So it's the continent-continent, really this should say continent-continent convergent plate boundary. I think on the test I fixed that, but right there it's not quite correct. So it should say continent-continent convergent plate boundary. The image to the right is an example of a transform plate boundary because the plates are sliding past each other. And here's a question for you. Is it a right lateral or a left lateral fault? It is imagine if you're standing there, what direction will you're looking at the fault. Which direction is the plate on the other side moving? It's moving to the left, right? And likewise, if you're standing right here and you're looking at the fault, this guy's going to appear to move to your left, okay? So that's a left lateral strike slip fault. Happens at a transform boundary. I hope you enjoyed today's lecture. I will talk to you next time. Have a good week, and just let me know if you have any questions or concerns about this class. Talk to you next time. Bye-bye.